Okay, then let's wait a second that people join. We had around 35 registered participants, and usually it is a very the rule of thumb is that more or less half of them take part in the webinar. So let's wait another minute to give people the opportunity to join, and then I will introduce you. Okay, I think the curve is flattening, so maybe we can start. We are around 20 participants. Let me stop sharing. Did I stop sharing the screen? Yeah. Okay. So good afternoon, everyone. Welcome to this NITheP webinar. This afternoon, we are very happy to have Professor Hugo Touchette with us. Hugo is Professor of Applied Mathematics at the Stellenbosch University, where he teaches probability and statistics, and from next year also machine learning as part of the Stellenbosch Masters in Machine Learning. By birth, he's Canadian, and he holds a PhD from the University of McGill. But before joining the University of Stellenbosch in 2013, he spent around 10 years at the Queen Mary University of London. Today, I'm very happy that Hugo will give a talk this afternoon, because last year, in a time where we were still allowed to fly around the world, I was at a conference in Banff, and in a talk of a colleague, I heard for the first time the reference to this paper, to a paper by Hugo on quantum processes with random resets. Yeah, and that was at that time new to me, and I thought, I know Hugo, so I need to ask him to give us a talk on the topic. And it took us a while to get it in place, but eventually it is today. Yeah, so Hugo, thank you very much. We are very happy that you agreed to give us a webinar on a topic that I thoroughly enjoy. Yeah, so thank you very much, Hugo. You know how to share the screen. And sorry, I know most of you are probably expert Zoomers. There is a question and answer facility. Please make use of that. And Ilya Sinaisky, who is a NITheP associate, will try to collate the questions and pose them to Hugo after his talk. So please, Hugo, you can share the screen, and we are looking forward to your talk.
Thank you. Let me share the screen. You see the slide?
Yes, perfect.
Okay. Okay, thank you, Francesco, for the invitation. I'm glad that we finally managed to find a slot for the talk. Thank you, Ilya, also for the background work for the Zoom. Let me take some time to wish all the best to Francesco in taking the lead for NITheP and for the continuation, NITEX. It's important that we keep alive and then we keep it active, and I'm glad to see that the center is moving to UKZN, and I'm sure that you'll be very active. It's already very active with all the Zoom talks that you're organizing, and the Friday morning talks also that you have on data. So we've seen some talks on COVID. The talk I'll be giving is not on COVID, so it's really on physics. I think it's important that we keep research even in this funny situation. So as Francesco said, I'll talk about reset processes, which are, I'll explain what they are, but I'll mention applications for classical processes and quantum processes. So this is the short plan. So this has to do with Markov processes. So I'm going to have to give a short introduction to Markov processes to everyone, because I'm not assuming that everyone actually listening has the background on this. And then I'll define what I mean by process with resets. And what I'll do during the talk, the goal is to present two kind of projects that I did on this topic. One being on spectral properties of reset processes, and the other one having to do with large deviations, which is the subject that I mostly work on. And as I said, I'll present examples of set processes for classical processes, but also for quantum processes. This is work that I've done initially with an MSc student at Stellenbosch in 2015, I think, Janusz Melan, who did a PhD, went to do a PhD in Leiden and now works in Leiden, also with Sanjeeb Sabapandit from India. And the work on the spectral properties is work I've done with a PhD at the University of Nottingham, Dominic Rose, and his group there, the group of Juan Graham. Okay, so I'll start simply with just some pictures of what we're dealing with. I think one stochastic process that most of you should or might have seen is the drunkard's walk. So it's a random walk where you start somewhere and then you take random steps in random directions, but also of random length, and then you just continue like this as if you're in a drunken state, and so you have your random walk. So this is the kind of basic example of a random walk. And if you have Gaussian displacements, then actually this defines Brownian motion. So Brownian motion is defined very simply, where you just iterate what I show here. This position, the next position is the previous position, plus a random displacements, which we take to be a Gaussian random variable. And so in MATLAB, you just write something like ren n, that's your Gaussian random variable. And then you set the time step to be the square root of dt, because in Brownian motion, you want the variance to grow like time. So this is the definition, really the defining property of Brownian motion, is that the variance of the random motion in 1D or in 2D or in 3D actually grows with time. And this is the basic recipe for this. And this has many applications in many different fields. In physics, for instance, this is the basic model of diffusion, for instance, of ink into water. This is the basic model also of thermal noise, which we call Nyquist noise. You see this random motion also in finance and the increments of financial stock. So it's pretty much everywhere. And in fact, it's used as the most basic model of noise that you can imagine, basically because of the Gaussian property. Now, the notion of reset in this context is that you start walking, and then after some random time, you just go back to the origin. And the idea that we have here, which I put in the abstract of the talk, is kind of searching for your keys. So you have your random search, you just walk around to try to find your keys. But if you go too far, or if you've walked for too long, you just think, oh no, they cannot be here. I have to go back to where I think they should be. And so you just go back to some original position, and then you start again walking from there. So at random times, you have an instantaneous reset to some position, which in the picture here, I take to be the origin. So this is a basic plot of Brownian motion or just a random walk. And then after some random time, I just go back to the origin, and this is the red line. And then I start the motion again, this is the blue line, and after some random time, I go again into the origin. So if I replot this, I'll get a totally different trajectory. And the way to generate this is very simple. Basically, what you have is a Poisson process superimposed on the Brownian motion. And the way to generate a Poisson process is you compare a uniform random variable at each time step with this constant. If the uniform is smaller than this, then you do the reset. If not, then you just do the Brownian motion. So adding reset is just really adding a Poisson process, so exponentially distributed time for enabling the reset. So this is actually used in random search. So Brownian motion is also seen as a model of random search, and people use reset in random search, and I'll discuss what it brings actually to the search. It's also used in other population, in other models, other random processes like population models, where you can imagine now you have random births and at random times, or you have deaths also at random times. Here I'm showing trajectory of a Poisson process that has only births, so there's no death. So the population is increasing randomly. And here I have 3 different trajectories of that process. And it doesn't have reset, but you can imagine that there could be some kind of catastrophe or some kind of wipeout or decimation that brings the population to 0 or to some low number. And this can happen at random times. And this will be also a reset. Reset is also used in queuing models, where similarly to a population model, you have random arrivals and random services. So the number of people waiting in the queue can go up and down, so randomly, but the queue can be reset at some point, at some random amount of time. So maybe you close the queue, or if this is a kind of internet server, you just switch off the server, and so the queue is cleared. And so this will be also a reset. And so reset actually has been studied not just in physics, but in these models in the 80s and the 90s. And it's just coming back now in physics because people have found some physical application. And this idea of having a reset actually can be declined in many different ways. So you have many different variants. You can reset at a fixed point, like I shown for the Brownian motion, but you can decide to reset at some point that you choose randomly. Instead of waiting exponentially, you can also wait with a random time that is, I don't know, distributed with a power law or some other distribution. And so you can have a different waiting time for doing the reset. In this case, then we say that the reset is non-Poissonian. It's even non-Markovian, and I'll discuss a bit about this. These are one particle process that I show, but you can imagine also having a stochastic process that involves many particles, and then at some point you reset the many particles in some state. For instance, people have actually looked at taking a simulation of the Ising model, and at random time, you just reset the spin, say, to the up state or to the down state. And this is also a reset. And everything I'll be mentioning actually is instantaneous reset. So after the random time, you just go back instantaneously to a fixed point, but you can imagine actually also going back with some other process to some other state. So it doesn't have to be instantaneous. The basic idea actually here is that you have a superposition of two processes. You have a random walk and then a Poisson process for doing the reset. And this falls into the field of probability theory that we call compound processes or switching processes. So it really goes beyond just the notion of resetting. It's just switching randomly between two types of motion. And in the present case, what I'll be talking about is that you have some kind of random motion and the other motion is just instantaneous reset. So this is what I'll focus on. Okay, so what I want to do now in the talk is to explain how we study this mathematically, how we actually define reset mathematically as a stochastic process, as a Markov process. So I'll start first by doing a quick introduction to Markov processes without reset. So this is not something that we study a lot in physics, but if you've seen quantum mechanics, it's very similar to quantum mechanics. So there's lots of analogies that you can build between the theory of Markov processes and the evolution of quantum states. And I'll pinpoint those analogies just to make the journey into the talk easier. So the basic idea here is that you have a state, which I'll denote by xt. So this could be the position of the random walk, the position of the Brownian motion. And then what describes now the probabilities about this motion will be the probability for the state. So this is the probability that the state is x at time t. Now, if the process is Markov, the time-dependent distribution would evolve in a linear way in time. So the partial time derivative of this time-dependent distribution would be given by a linear equation. So there's some operator that will act on this time-dependent distribution, very similarly to the Schrödinger equation for the wave equation. The difference here is that we're dealing with probability and not with probability amplitudes. So everything is classical, everything is real, there's no imaginary number. But the basic equation for the evolution of the distribution is a linear equation. And I'll be dealing with ergodic systems. So ergodic systems have a stationary distribution, which is unique, and it's the time-dependent distribution. So it's the one that has eigenvalue 0. So if I act on this distribution, I get 0 because the time derivative is equal to 0. Okay, now what is that L? L actually depends on whether you study a discrete system, so a system with discrete states or continuous states. So a system with like discrete states, like a population model where you can increase from 0 to 1 to 2 to 3, that's a discrete process. We call this a jump process. So we have discrete states evolving continuously in time. The Q is of the same nature, population model. So in this case, L will be a matrix. I'll just show in the next slide what L is. L is just basically the matrix of the different transition rates that you have between the different states. If you're dealing with a continuous process, so a process that has continuous state evolving continuously in time, like the one I show here, this is a kind of diffusion model where the state is continuous, we call this a diffusion. In this case, we'll see that L there, the generator of the evolution, is a differential operator, just like in the Schrödinger equation when you're dealing with continuous state. Okay, so this is what I'm going to do in the next page. So if I have a jump process, so this is again a process having just a discrete number of states. So I could have that state, and then after some time I can jump to that other state. Oops, sorry. And then here, after some other time, I can jump to another state. But the point again is that I have a discrete set of state. In order to describe that process, what I have to do is to give the transition rates between the states. So this is the transition probability from going from state C to another state C prime. And that rate is the probability per unit time of making the transition. If I give all these rates, I completely describe the process. And the generator will consist of these rates. So the generator will be a matrix because I have rates between all the states. We'll have those rates in the off-diagonal part. And it's something actually just so mathematics is that you also have to fill the diagonal part with what we call the escape rates. The escape rates are just the sum of all the transition rates from a given state C. So you just sum all the rates. So it's really the full transition rates from leaving C. And if you put this in the diagonal, then you actually construct the generator. So mathematically, this generator will give you the evolution of the time-dependent distribution. It's a matrix. So imagine, for instance, when you have spins, the Hamiltonian is a matrix. Here I'm dealing with a discrete state, so the generator is a matrix. Now, if I deal with something that has a continuous state, then I can represent that evolution in a very different way. In fact, I can write what we call a stochastic differential equation, which will be a differential equation plus some noise, which is a Brownian motion. So this is a difference equation where the increment of the state will be given by some deterministic part, a force field or something, and then it has a random part, which is an increment of the Brownian motion. In this case, the generator now is a differential operator. It's a linear differential operator that has two parts. It has a kind of advection part that comes from the force field and a diffusion part that comes from the Brownian motion. And this is the generator that will actually evolve the distribution according to my equation here. And in the diffusion case, we call this the Fokker-Planck equation. But again, I have the evolution equation, which we call the master equation, or the Fokker-Planck equation, depending on whether I deal with discrete state or continuous state. Okay, so that's an introduction of to Markov processes, basically in 2 slides. I actually give a full semester course on this for honor students at Stellenbosch. But this is all we need actually for understanding reset process. So what is a reset process? Again, the way you picture a reset process will depend on whether you consider a discrete state process or continuous state process. So I'll start first by the jump process. So in this case, you want to reset at some state. So you just pick that state. We'll call it C0. That's our reset state. And what we have to do is just to add rates for any other state to actually reach that reset state. And then we give it some rate, which I'm going to call gamma. So the probability to go from any other state to that reset state in time over a time dt will be gamma times dt. If you do this, this will define a Poisson process, and this will define an exponentially weighting time for all the states to fall eventually in the reset state C0. So this is very easy. For a jump process, all you're doing is to add more rates for doing transition to that particular state that you think of as being the reset state. For the diffusion, it's slightly more complicated. So for the diffusion, what you have now is a continuous state. We will select a reset state. So I'm going to call it x0 now. And what you're doing is this superposition idea that I mentioned before. If what you do is that you throw a uniform random variable over a time dt, if that uniform is smaller than gamma times dt, you do the reset. So that means that your state now becomes xr. Actually, I should have called it x0. It's just that x reset here. I forgot to change the notation. If you don't have this condition, then you do the normal motion. And the normal motion will be the new state is the old state plus the differential equation part. So that's the deterministic part, plus the random displacement, which is square root dt times a normal Gaussian random variable there. So that's the normal displacement. So you see that in the picture, Then on the blue part, I have normal Brownian motion. And then at random times, I have that red line that brings me back to the reset state, which I chose in this case to be 0. And after, I just do the Brownian motion. But all of this is done in a time-stepping way. At every time dt, I check whether I should reset or do the normal Brownian motion. But the overall result of this is that I will reset at exponentially distributed time. So this is the way you do this at the level of the stochastic process, at the level of the simulation. What you can show is that if you introduce that kind of reset, it will change the Fokker-Planck equation. So it will change the master equation. So this is our original master equation. This is how the probability evolves now without reset. If you put reset, what it does is that it creates a sink because every state can fall into the reset state at a rate gamma. So this is a sink. And then once the state is there, the state is actually on the reset state. This is the source. So once you're on that reset state, you'll start doing the motion emanating from that source. So now the Fokker-Planck equation will have a sink term and a source term that will actually cancel each other exactly. So I conserve probability throughout. There's no, the particles do not disappear or are not killed. They're just being resetted. So this is the Fokker-Planck equation with reset. Okay, I'm not going to derive this. This is just the way it is. Now, one thing that's really interesting with the reset process is that there is a probability current because all the states actually are eventually reset to x0 and they start moving from that reset state. So over time, I have this probability current. I have this particle current of particles going from away from 0 to 0 and then starting again from 0. So you have to imagine that there's a kind of current from the sink to the source. And this is the effect of reset. Okay, so this is how you define mathematically a reset process. And I'm going to give a basic example as to how you use now the reset Fokker-Planck equation to find a stationary distribution or order probabilities. So this is an example that was given in 2011 by Martin Evans and Satya Majumdar, who actually put back this notion of reset process on the map. And from their studies, many people started studying this in physics. So the most basic process you can imagine is Brownian motion in which you add reset. So if there's no reset, then Brownian motion is just a diffusion equation. The evolution of the time-dependent distribution is some d, some constant, which is the noise power, and then multiplied by the second derivative of the distribution. So this is the heat equation. This is the diffusion equation. And what I'm going to do now is to put the reset. So I have the sink with the minus gamma. Gamma is the rate of reset. And I have the source, the delta, at x0, which is the reset state. What you can do now is to say, what is the stationary solution of this equation? This is a well-defined partial differential equation with a source and a sink. It's slightly more complicated to solve than the normal diffusion equation, but you can do it. It's not too difficult. It's in the paper. And what you find is that there is a stationary solution. It's unique, and it's got an exponential form. It's exponential form around the reset state. So here I'm actually plotting this stationary distribution for a reset at 0, and then you see it's an exponentially decaying distribution with some rate that depends on the reset state and the noise power. This is interesting in this case because if there's no reset, there's no stationary distribution. Brownian motion actually diffuses to infinity, so it doesn't have a stationary solution, it doesn't have a stationary distribution, but the reset actually creates a stationary solution. And in a way, you can see the reset as a weak confining because it takes particles away from 0 and then brings them back to 0 at some random time. Okay, so there's no stationary distribution without reset, and then reset can be seen as a kind of confining. It can be seen as a kind of force, but it's not a force. It's a random, in a way, confining of particles that moves away from 0 to 0, as we see on this. So it's not quite like adding a potential. If you add a potential to Brownian motion, you also create a stationary distribution. But here we can create a stationary distribution without putting a potential, just by bringing reset into 0. Right, so this is a basic application that shows what is the effect of reset, how you can find this from the reset stochastic differential equation or from the reset Fokker-Planck equation. What I want to do now is to present what I said before. So 2 projects that I've done on reset process. So many things have been studied about reset processes, including stationary distribution, mean first passage time, time-dependent distribution. And so when I was looking at this, then we were discussing with the colleagues and to say, okay, what can we do that was not done? And then one project that we that we started studying is the spectral properties of processes that have reset. Now, how can we talk about spectral properties? Remember that the evolution of the time-dependent distribution is a linear evolution equation. So there's a linear operator, which for a diffusion is a differential operator. So I can talk of the spectrum of this equation. I can talk about the spectrum of this generator, and this is what I want to do. And so the goal is to actually calculate the spectrum of a generator, then put reset and try to understand how the spectrum will change with the reset. And to make ideas actually clearer, I'll make analogies now, direct analogies with quantum evolution. So for a classical stochastic system, this is what I have. I have the linear equation for the time-dependent distribution. As you all know, for a quantum system, what I have is the Schrödinger equation. So the wave function will evolve in time according to some operator acting on psi, and the operator is the Hamiltonian in quantum mechanics. And for a system with a continuous state x, that Hamiltonian is also a second-order differential operator of this form. So I have a kind of diffusion term plus a potential term, which is the potential acting on the particle described by psi. Now this is a very strong analogy. I have really the same structure, but all that changes is the fact that here I have a second order differential operator that is not emission. It's not emission because of the F part. The Hamiltonian is Hermitian because it's got the Laplacian, which is Hermitian, and then you have the potential, which is a scalar. The fact that I have an emission for quantum mechanics, as we all know, means that I have a real spectrum. Now, for Markov evolutions, I don't have this property. In general, the evolution generator is not emission, and so in general, the spectrum of that generator is not real. However, that generator for the Markov case always has a dominant eigenvalue, which is a 0 eigenvalue, and that eigenvalue is trivially related to the stationary distribution. I always have that 0 eigenvalue for Markov processes if I'm dealing with ergodic processes. I don't have this property for quantum system. It's not something actually needed. It's not something that's constrained in the physics of the system. In quantum mechanics, what you have is depending on the potential V, I have a ground state and I have a ground state wave function associated with the minimum energy. And the value of that energy is actually arbitrary. So I don't have a maximum or minimum eigenvalue as such. But for Markov evolution, I have this property. So the spectrum actually of a Markov evolution is I have always that 0 and then negative eigenvalues. And so what I have in terms of an eigen decomposition of the state is a kind of decay dynamics. I have the 0 value part, which is the stationary distribution, and then I have a sum of all the other eigenvalues which are negative, so they decay. I have a decaying term here with eigenfunctions that will tell you how that behaves in space. So for an ergodic process, the sum actually decays exponentially to 0, and all I'm left with is the stationary distribution. So that's the decay to the stationary distribution. For quantum mechanics, I don't have this at all because the eigenvalues are real, and so I have a kind of rotation in the complex plane of the exponential, and then I have the eigenfunctions for the potential. So I have 2 different dynamics, but what's common in both, again, is the linear structure of the dynamics and the fact that I can really represent the dynamics in terms of eigenvalues and eigenfunction. But the difference, again, is that I have, for Markov, in general, non-emission, and for quantum, emission. Of course, if you consider now quantum open systems, you can have non-emission dynamics, and I'll discuss this when I get to the quantum applications. Okay, so here's the project now. So I want to study a Markov evolution as a linear evolution. I want to look at the spectral elements of the generator L, and I want to see the effect of the reset on the spectrum. Now, to make to make the ideas closer to quantum mechanics, I will actually write the master equation in a quantum way. So that time-dependent distribution, although it's not a quantum object, I'm going to write it as a ket because it's a vector real. And I imagine that I have an evolution over some set of states, which I'm going to denote C. So I have a complete set of states C, and I can just decompose that vector for the time-dependent distribution as the probability to be in the state C at time t, and this is the vector C. This is just a vector corresponding to that configuration C, or that state C. So I can just write this in the ket notation if I want, because this is obviously a kind of evolution of a vector given by a matrix or a differential operator. So I'm going to think about the discrete case where I have a discrete number of states that just make things easier, but then I'll see how we can apply this for continuous state. So for a discrete set of state, the generator, as I mentioned before, is a matrix, which I can also represent in a quantum way as a matrix in the following way. So I have the rates from going from a configuration C to C prime, and this is the matrix element C prime C. So this is just, it gives the position in the matrix of C prime C. But the notation is, you can also view it as going from C, so the bra C, to the ket C prime. So you have a jump in this case. So this is a jump part in the generator matrix. And this is a diagonal part, which is just, again, the normalization of the generator to make sure that I have a station distribution. I put the jump rates for each of the states C. So this is the representation of the matrix. I have a matrix with the transition rates. It's got a diagonal part, enough diagonal part, and the dominant eigenvalue of this is 0, and the eigenvector corresponding to this is the stationary distribution. So it's a matrix acting on vectors. I can define the spectral elements, but because it's not an emission, I have to be careful. I have to consider right eigenvectors and left eigenvectors. The eigenvalues will be the same, related by the complex conjugate. So I can define the right eigenvectors. I'm going to have I of them. I'm going to have, say, n of them, depending on the size of the system. And I have the eigenvalues related to each of the right eigenvectors. L can also act on the other side as a transpose. And so this will be a left eigenvector, Li. I have the same eigenvalues. I have the same spectrum, but the eigenvectors, the left eigenvectors, are usually different from the right eigenvectors. So here's the spectrum. So I have a sequence of eigenvalues. As I said, the largest one is always 0 for a Markov process. And then I have negative eigenvalues, which I can order lambda 2, lambda 3, so on. And I'm going to have n of them depending on the state, the size of the system. And as I mentioned, the eigenvector related to the first eigenvalue is the stationary distribution. And for the left one, actually, you can show it's very easy, that the left eigenvector related to the eigenvalue 0 is what we call the all state, is the sum of all the vectors C. And then we denote this by the bra, just minus. We call this the all state. This will be very important. Okay, so this is the linear structure of a jump process. This is the linear structure of an evolution, a classical Markov evolution over a discrete set of states. What I'm going to do now is to add reset. So how do we add reset? So I've mentioned before that if you want to add reset, what you do is that you choose a reset state that will be the C naught. And what you do is that with rate gamma, you just jump from everywhere to C naught. So everywhere is the all state. So that's from all state, I can jump to C naught with a rate gamma. And this is the diagonal part that renormalize the generator just to make sure that the eigenvalue, the dominant eigenvalue, is still 0, and then I have a stationary state. So this is really just like the escape rate. Again, because you've added new rates gamma, you have to change the escape rate in the diagonals, and this is what it does. Okay, now I'll present the result. If I add this reset in the generator, how are the eigenvalues changing and how are the eigenvectors changing? So first off is that the dominant eigenvalue doesn't change. I still have a 0 eigenvalue because starting from an ergodic process with reset, I still have an ergodic process with a stationary distribution, so I have an eigenvalue 0. This is conservation of probability, basically. Then for all the other eigenvalues, what's really interesting is that the effect of the reset is just to shift all the other eigenvalues in more negative. So the original eigenvalues, which are the 0 reset eigenvalues, are just shifted, all of them, by minus gamma. This is something you can prove by just playing with this new generator having reset. So basically what you had in this is more dissipation. You have the system will go quicker to the stationary distribution, which is modified. Okay, so this is the main result, actually. This is the result for the spectrum. What we can show also is that the eigenvectors are changed, but not the right ones. The right eigenvectors, except for the first one, are not changed. So all the right eigenvectors, except the stationary distributions, are the same whether you put reset or not. The left eigenvectors, however, are changed. So the one related to the zero eigenvalue is still the same. It's still the all state. But the one related to the other eigenvalues are actually, these are changed. So the result is the following. So you have the original left eigenvectors, and they're modified with the gamma, the reset, in the following way with the reset, with the all state. So it's a kind of projection with the gamma onto the all state. It looks a bit like first order perturbation in quantum mechanics, but this is actually not a perturbative result. It's an exact result that's true for all the gammas. And now the more interesting result, beside the eigenvalues, is the stationary state. So by putting reset, you do change the stationary state, and it changes in the following way, very similarly to the left eigenvectors. It's you take the stationary state without reset, and then you just perturb it now in this way by projecting with the gamma onto the R states, which are the same actually, again, as before, with or without reset. And the perturbation is weighted by the change in the eigenvalue. So this looks again a bit like perturbation theory, but again, it's an exact result. So the results that are really worth noting is the first one with the spectrum. So I'm shifting all the eigenvalues except the first one. So I'm increasing the gap. So I actually increase dissipation and relaxation to the station. And the stationary state itself is modified with the gamma in the following way. So these are the main results of that work that I've done with the group in Nottingham. So this is the reference for the paper if you want the calculation. What I'll show now is just a basic application where we take again Brownian motion and add reset. So I've shown before how to get the stationary distribution by solving the reset Fokker-Planck. What I'll do now is I'll get the same distribution but using the spectral results. I know the stationary distribution before, and I can find out the distribution with reset. What I'll do as a trick is that, well, first off is again, I have that diffusion equation. So the L, in this case, the generator is just the Laplacian, is just the second order differential applied to Px, that's the generator. This is emission now, so I know I have a real spectrum. And it's a bit like quantum mechanics. I cannot define the spectrum over the whole real line. There's no real eigenvalue there. But what I can do is I can confine the motion into some box of size L. So I take it L minus L over 2 to L over 2 with periodic boundary condition. And so what I have really is like a free quantum particle in the box with periodic boundary condition. With Fourier transform, I can diagonalize this, so I can find the eigenvalues. These are the eigenvalues. And the eigenfunctions are just the Fourier modes over the box. Now, because the generator is Hermitian here, the right eigenfunctions are the same as the left eigenfunctions. So I don't have now that difference between left and right eigenvectors. They're the same. And now I can just plug into these vectors and the eigenvalues into the formula I had before for the stationary distribution. Then I have a sum over the different modes weighted by the eigenvalues, shifted by the gamma. I can take the box bigger and bigger like we do in quantum mechanics now to replace the discrete Fourier transform as by the Fourier transform. And if you do the integral of the Fourier transform, then you get that exponential state, the exponential stationary distribution, the exponential of minus absolute value of x, just like I did before. Okay, so this is a kind of just check now, a sanity check to check that the results that we had for the spectral properties of the reset motion will give you the result that we were able to get using the reset Fokker-Planck equation. So in the paper, we have other examples. There's a random walk, but there's also examples related to quantum physics. And here it's slightly more complicated. So I won't present all the details into this, but I'll just give an idea of why we can also treat quantum systems and put reset onto quantum systems. So the starting point here is that we'll be dealing with an open quantum system. So a system interacting with environment. And then we know in this case that we can represent the evolution of the density matrix now as a linear equation involving some kind of generator that's called the Lindblad operator. And the Lindblad operator will have two parts. It has the closed evolution part that will actually be realized if the system was not interacting with the environment. So this is the usual quantum evolution for the density matrix. And this is now a more complicated term which models the coupling with the environment in terms of what we call jump operators, which are the JJ terms there. So this is more complicated. I don't want to go into the details of this. This is really how you model the evolution of a quantum system interacting with some big environment, infinite environment. The difference with the master equation is now rho is not just a distribution, it's the density matrix of the quantum system, and H now will be the Newtonian, so that will be some huge matrix, and now you have these JJs according to which environment that you take, according to what model that you'll have for the environment. The point again is that this is a linear equation, so I can define spectral elements, but because I'm acting on a density matrix, I don't have eigenvectors, I have eigenmatrices. So L as a linear operator is acting on matrices, and so I can define now eigenmatrices with the eigenvalues. So these are the matrices that don't change upon the action of L. And because L is in general non-emission, I also have right eigenmatrices, and I also have L eigenmatrices that will be obtained by taking the adjoint of the Lindblad operator. The spectrum is the same up to complex conjugate, but the eigenmatrices, the left and right, will be different in general. And now what I want to do is to put resets on it. So how do I put resetting? The game is the same again. I will define a reset state where I want to go to after a reset, and I'm going to do the jump, the dynamics, by defining in the same way as I have now environment operators. I'm going to have a reset operator which will be acting from all states I to the reset state with a rate which is gamma, and here I have square root gamma because we're dealing with quantum amplitudes and not probabilities, so the rate is square root gamma. But you see that this is a kind of open system evolution that takes you from any state or any state in the complete decomposition of the system to the reset state. And what you can show now is that having that operator, if you plug it into your Lindblad, what you have is that the Lindblad with reset will be the original Lindblad operator plus two terms. You have the term which is basically the normalization, and then you have the sinc term that takes the density matrix down to the reset state with a rate gamma. So this is the form really of the reset Lindblad. Okay, so you can play the same game as we played before. You can define the spectral element of the Lindblad without reset, then try to find the spectral element of the Lindblad operator with reset, and the results are the same as we had before because the structure is the same. In particular, the dominant eigenvalue is not modified, but the other eigenvalues will be shifted by the gamma like we had before. So I'm not going to present the results for this. They're really the same. What I want to do is just to show one example of a quantum system in which we have reset. In the paper, we actually present two, and I'll just present the simplest of the two, which is a quantum random walk on a chain. So what you have is you have a kind of a chain with periodic boundary conditions. So you imagine a lattice that just is closed at the boundaries. And then you have a random walk from a state x to x plus 1 or x plus 1 to x. And so you have different jumps. Here I'll take that the system is actually closed. So there's no environment as such, but I have reset. And reset, as I said, it's a bit like introducing an environment because if you want to put reset, you have to define these jump operators, so these system operators that are the reset operators. So this is the Hamiltonian. So the Hamiltonian has the sum over all the states. This is going from x to x plus 1, so you're moving right with rate gamma, and this is going from x plus 1 to x, so you're moving left with the same rate and periodic boundary condition. What I'll do is that I'll reset at the position 0. So this is the reset operator. I have a state corresponding to any kind of my complete decomposition, and from there I can go to 0 with a rate gamma. It's not the same as a projective measurement. This is not actually measuring the system at the state 0. this is really introducing a kind of environment operator that will bring it in a Lindblad way, the state to 0, but I have a coherent evolution given by the Hamiltonian on which I superimpose a kind of system dynamics bringing the reset. And again, this is not the same as a projective measurement. So here I show the results. So you can solve this system exactly with the reset, which is quite nice. This is in the paper again. And what I'm showing here is the density plot of the density matrix for 2,000 sites. So I have the site 0 in the middle. I can go to 1,000 sites on the left, on the right, and 1,000 sites on the left there, and I reset at 0. So I should see more probabilities or more amplitude at 0, and this is what you see. But because this is a quantum system, it actually has coherent lines there where you have constructive interference coming from the quantum random walk. But if you put more reset, so this plot here is for reset equals 1, and this is for the reset rate equals 5. So I have more reset. And what you see is that you have more localization around 0 because you're resetting there. Here in the bottom plots, what I'm showing is the probability to be at the site I as a function of the site position from 0 to 1,000. And I have the quantum result, which is the purple line. And I compare this with a normal classical random walk in which I reset at 0. And then you see there's a difference because the quantum random walk has coherence that the classical random walk doesn't have. So the probability to be on each of the different sites is not the same. And what I see again is that I have more localization in the quantum case than in the classical case. So I have that localization at 0 that comes about because I have that gamma to go at the state 0, at the site 0. So this is actually a log linear plot. Okay, so it's quite a huge difference actually when you compare the two distributions. Okay, so that's the quantum application. I actually use more of my time to describe those. I want to describe also, I want to turn now to a different project, which is something that I did initially even before the spectral property, which I did with the master student, Janusz, which is to look at how the large deviations of a stochastic process are modified when you put resets. So I'll go quickly on this. I'll just give the basic ideas and then you can have a look at the details in the paper if you're interested. The idea here is that we're not really interested in the process itself. So we still have a Markov process, which could be a model of some physical diffusion or some many particle process that evolves in time. But what we want to study is not X itself, but something that we call the observable. It's some time integrated quantity. And then we want to find the distribution of this. So we have some process. I see the process here. And I want to calculate now the distribution, not of X, but of this observable AT, which is a time integrated functional of the process. Finding the distribution is very difficult in general, but there's something that saves us, which is that in the long time limit, the distribution often has, I would say like in general, it has this exponential form. So it decays exponentially with time with a certain exponent that we call the rate function. So the distribution in that case, in the long time limit, is all described by this function I of A that we call again the rate function. And the game in this case is to try to calculate the rate function to characterize the likelihood of the different fluctuations of the observable, to see how the observable actually fluctuate. In general, the observable will have a 0. This is where the distribution concentrates in long time limit, and it has a certain shape that tells you really like the shape of the distribution on the exponential scale. What's interesting is that, so you can do this in physics, but it's done in other contexts. In physics, if you look at non-equilibrium system, that observable can be a physical quantity like the work or the heat exchange with the system. It can also be something that we call the entropy production, which measure how non-equilibrium the system is. And if you look at the equilibrium system, then the rate function can be related to the entropy. So there are many relationships or links between this formalism of large deviations and thermodynamics and statistical mechanics. For instance, the appearance of a Legendre transform, we'll see this in the next slide. So this is a nice formalism that actually speeds up the calculation of this distribution to get an approximation of the distribution in an easy way, because finding the distribution, again, is just impossible. Okay, so how do we get this rate function? So I'll go very quickly on this. This is a bit technical, but you can find all the details in this paper, which is actually a bunch of lecture notes that I give to a summer school in 2017. So the idea is, instead of looking at the distribution directly, you look at the generating function. So this is the expectation of some exponential. And if you take the limit there, this gives you a function that we call the scale cumulant function, a scale cumulant generating function. There's a basic result in large deviation that tells you that if you can calculate this lambda k and it's differentiable, then the distribution that you're interested has that exponential form. And moreover, the rate function is a Legendre transform of the lambda k. So this is very nice. Moreover, for Markov processes, you can actually calculate the lambda k as an eigenvalue. It's the dominant eigenvalue of a modification of the Markov generator. So if you pick a particular system, then that defines your Markov generator. If you pick an observable, that's your f. Now for the basic k here, you choose your k, which is just a real parameter. Then you change the generator. That gives what we call the tilted generator or the tilted operator. If you find a dominant eigenvalue of this, this is the scale cumulant generating function. So to find the large deviation rate function, what you do is that you solve a spectral problem. You find the dominant eigenvalue of the tilted generator. You do this for all k. You take the Legendre transform, and then you get your rate function. So it sounds a bit complicated, but it's not so difficult. And the basic point is that the rate function is the Legendre transform of that scale cumulant generating function, this thing. Okay, so this we've done for many years. People have applied this formalism to look at the fluctuations of many different observables of many different processes using this spectral idea. And so what we want to find now is how the large deviations are modified if you have resets. And this will be basically more or less like the last slides I'll present in terms of results. I'll go very quickly on this. So what we do, we're not actually attacking the spectral result directly. What we do instead is that we look at the generating function. This is the generating function I need to calculate for the observable AT. And this is a particular form, because if I look at the reset structure, the reset process is actually, again, a superposition of free motion and reset. Free motion, reset, free motion, reset. Now, when I have free motion, the process is not actually affected by the reset. So if I look at the reset generating function, I can decompose this as the generating function as if I had 0 reset, or maybe the generating function as if I had 2 resets, 3 resets, 4 resets. So I can decompose now the generating function as a superposition over all the possible resets I can imagine. Then I have the probability of the resets, and then I have the different times at which the resets happens. But the point again is that in between reset, the generating function is the generating function without reset. So I can relate the non-reset generating function to the reset generating function. And this is what we call the renewal representation. That reset process is really a renewal process. It's a process of free motion interspace with the reset. And this is what enables us to actually write the full generating function in this particular form. So this is, I don't want to explain all the details of this. It's just something we can do. It's something that people have looked before. There's a subtlety here, which is that the sum of all the reset times are constrained to the full time t. So I have that delta function that constrains this. So that makes this very difficult to treat. But whenever you have a constraint like this, what you do is you take a Laplace transform. So instead of looking at the generating function itself, I'll take the Laplace transform of it, and the renewal representation now simplifies, and it's just a geometric sum. So I have this result, which is the main result that we want to study. So this is a very interesting result because it says that the Laplace transform of the generating function with reset is just a transformation of the generating function without reset. So the G naught there is the generating function without reset, whereas the G with the gamma is the generating function with reset. And you see it's just a basic pole transformation of the generating function without reset. So what I can do is that I can do the large deviation without reset. That's the generating function here. I can shift it like this, transform it like this, and I get the new generating function with reset. And for the purpose of obtaining large deviations, all I care really is the long time limit. And so this will behave exponentially on this side. And at the level of the Laplace transform, if you have an exponential behavior, it just means that you have a pole in the Laplace transform. So the upshot of this is that the large deviations will be obtained here just by looking at the dominant pole of the generating function with reset, which I can do. So I think here actually, I think I'm going to skip the application. So there's an application in the paper. So this is the work I've done with the master's student at Stellenbosch in 2015. Yes, that's the reference I have here. I'll show you the reference at the end again. So what we did is to look at the Einstein-Ulevik process, which is a linear process. You look at the area of the process, and then you can put the reset and then get the large deviation function with and without reset. I'm not going to discuss this. It's not really important. If you're interested, then you can find all the details of the calculation and the interpretation of those results in the paper as well. So what I'll do is I'll finish just by mentioning that this is just the beginning of many other results. If you're interested in this kind of reset process, there's lots of papers that have appeared recently, driven in large part by the work that was done by Majumdar and Evans in 2011 to study diffusions with reset. So in the 80s and the 90s, most of the reset process that were studied were jump processes for population and for queues, but now people are more interested in reset diffusions, so continuous state that evolves continuously in time. And then you can study this in many different ways, and people have worked a lot on this in many different ways, studying different quantities, different scenarios, different variants. So I've worked myself actually on different projects looking at phase transitions and fluctuations of reset process. This is the other paper I'm mentioning here. But people have looked at variants again of the reset process where you do not reset with the same rate at the different place, but you could have a space-dependent reset. So in this case, gamma now is a space-dependent function. So you can do this. As I mentioned before, you can also reset at non-exponential reset times. In this case, you have a non-Poisson process. And as soon as you have non-Poisson, then it becomes non-Markovian, so it's a bit more difficult. I've mentioned that you can also imagine a reset where you do not go to the reset state instantaneously in time, but it goes according to some process. Once you get to the reset state, you could also have a random waiting time there. So these are all different variants that you can imagine, and people have studied this. One important thing which I should mention before I finish is this idea again of a random search. So Brownian motion is used as a way to do actually random search, for instance, in machine learning to optimize model or to find a minimum of loss function, then you can use random search. And in many cases, you don't put reset. So what people have done is that if they wanted to see if by putting reset, you would be more efficient at searching something randomly in space, and the answer is yes in general. And the way you do this is you put the random target in space, and then you start your random motion, and then you compare the mean time to reach the target with and without reset. And what you can show is that that mean time is usually smaller with reset. So usually in general, under some conditions, it's not true, I mean, there's no free lunch, but under some general conditions, a random walk with reset will find the target quicker than one without reset. So this is again the idea of looking for your keys. So it makes sense to go back to starting the position when you're looking for your keys. It just reduces the mean time to finding your keys. Okay, so this is as much as I'm going to say about reset process. If you're interested in this, I can suggest this recent paper, which is a review paper by Martin Evans, Sachin Majumdar, and Gregory Scher, who've worked a lot on this type of processes. So this is a very comprehensive review paper. And here I'm presenting the 3 references for the work I've done myself on this process. And if you want more references on large deviations or other projects I'm doing, then I put the address of my webpage there where you can find all the details. So I'll finish on this. Thank you for your attention.
Yeah, Hugo, thank you very much for the excellent and very, very interesting talk. I see that there are a few questions. Would you like Ilya to lead us to the questions, please?
Yes, please.
Okay, so I think there are a couple of questions which probably, I don't know, I just don't want to disturb you while you were talking, but there are a couple of clarifications which people were trying to ask you.
Okay.
So the first clarification is from Christian Rover, and he's asking, in the Fokker-Planck equation with sink and source, is it obvious that this form maintains the total probability? And he is a little confused because he cannot cast it directly to the continuity equation.
Yes, no, it's not obvious, but it does. So this is the Fokker-Planck equation with sink and source. It's not obvious. You can see it in different ways. You can discretize the Fokker-Planck equation in space, so then it becomes that jump process in which you've added all the rates in some row or some column. If you take the continuous limit, this is what you get actually. So it's clear in the discrete case that it does conserve probability, and if you take a continuum limit, then you get this also. But it does. So there's probability is conserved, and there's a probability current as well.
Okay, so there is also a first clarification, want to ask for clarification from Jan Low. And the clarification is, can you just mention the quantum version of the reset process again? Is this done just with the Limboth equation and the given jump operator, which is act as a reset?
This is the one here. So I'm not the expert on quantum system. Jan actually will know that I'm an h bar equals 0 guy. So I'm forcing myself here a bit. So I have the Lindblad master equation with the Lindblad operator. I think Jan will understand this one. And so what I do is that I just add more of these system environment interaction operators. So the phi I here is actually the basis I'm using for describing the system. So it's not the particular state of the quantum system. It's just the basis I'm using. So from any basis vector, I can go to the reset state that I've chosen with some rate gamma. So this is what I'm doing. So it's a jump operator. It looks like a projective measurement, but it's not one, right? Because it's going to enter again just as an added system environment interaction operator there. And here actually, I've shown that this is the effect of putting those there. There are many steps I'm not showing here. This is actually the final simplification of what the Lindbladian would look like. But there are many steps which are in the paper. So what I would do is I would put all these jump operators in the Lagrangian, but then I can simplify a lot of these of the sum there, and what remains here is just the gamma with the trace of the density matrix, and this term actually, which is the reset term. The term is more or less just the conservation terms to conserve probability. I don't know if this is clear.
Okay.
Yeah,
but I mean, like, okay, but essentially with this, sorry, can I just comment if I understand correctly? So essentially you just wrote the Lindbladian terms and you sum over i's, and that's exactly what you get these two terms.
Yes.
Is it correct?
Yes.
Okay.
Yeah.
So, and now there is one more follow-up from Jan, and the question is, next, have you considered resetting not just one state, but the multiple different states with a specific probability? I know you said that in the quantum mechanical case, it's not the same as projective measurement, but this also could act as a reset in a way. However, to set of states with probability given by the Born rules. Would you be interested to see if one could model this with a reset process?
Yeah, I think it's got a good point. I think actually Michael Kastner mentioned something like this too. In the paper, actually, we have an example where we don't reset to one state, but we can reset to two states. And if you go to the definition, you can include this also as a different rate, because here we have, where was it? So you don't have to choose only one state for the reset. You could choose many states. You just had different rates then for going there. So if you have multiple states, then you're going to have here a gamma 0 for that reset state. Then you're going to have another gamma 1 for another reset state. So you can do this by having now multiple reset operators for different psi that you choose. So you could have a reset 1, a reset state 2, and then you just go with different rates to those. These won't, they will be different from projective measurements again. Right, so this kind of interaction is a kind of partial measurement. I mean, Jan would know this too, more than I do. In fact, it's a partial measurement of the environment on the system that that just drives the system in an open way. And this is how we model this mathematically. So this comes from the studies of open quantum system. You could also put projective measurements into the picture if you wanted. You could picture this as a kind of reset if you wanted, but it will be different from what I presented here. So I'm not sure actually how the spectrum will change in this case, or if it changes at all, because projective measurement doesn't really change the spectrum. It's just a projective measurement. So there are many declinations or many variants that you could consider, and they could be very interesting. I guess it falls into this idea also of quantum control, where you're trying to control a system with the environment, either with projective measurements or with partial measurements, or by driving the system with also environmental operators. And reset can be seen then as a different kind of control action onto the system.
But if you're going to have a projective measurement, won't you lose the linearity in that case?
Yeah, you would lose the linearity, yes.
Yeah.
So that's why I'm saying that this is not the same as putting the resets there, because you're not changing the spectrum, right? We don't see projective measurement as a dynamics. It's something that's separate from the dynamics. We have dynamics and then projective measurement, which is another type of action.
Okay. Can I ask another question? So that's from anonymous attendee. On the slide 14, so on the next slide, how is the probability of being in the site I changed if you increase the number of site n? So how it scales essentially?
This I don't know actually. I'm not so sure actually. If you look at the classical random walk, actually it's very similar to the Brownian motion with reset. So it's an exponential, right? So this is why you have the straight line here for the blue curve, not the purple curve, because we have a log linear plot then. So the straight line is more or less the decaying exponential. So if you increase the number of sites, then you're just increasing the extent on which you have that that decaying exponential. With the quantum, then there's more localization around zero, coming from the coherent dynamics, but I'm not sure how that curve actually depends on the number of sites. The solution in the paper is the exact solution, so you can actually put, it's given for any n, it's just that the plots there are given for 2,000 sites. So I don't quite remember on the top of my head. I would have to check with the paper.
Okay, so we have one more question from Xina Mazia, I hope. Yeah. Okay. How does the reset process search time compare to the other procedures in the case of more than one target?
This I have no idea. I'm pretty sure it's been studied. So there's quite an extensive literature on random search with Brownian motion, random search with random walks. That literature actually is exploding now also with machine learning applications. And actually also originally the idea of putting reset was linked to the idea of search. So again, with the analogy of searching your keys. And the first study was for a fixed target. So one target placed at random, and then you look at the mean first passage time, which is a mean time to reach the target. If you have multiple targets, I don't know how it behaves. This is a different problem, but I wouldn't be surprised if it's been studied. What I will refer Mazia to is the review paper. The review paper actually discussed extensively this application of random search.
Okay. And there is a couple of questions from Camille. So Camille is asking, this reset process reminds me of a quantum Zenon effect. Did you study this parallel?
I did not. Again, I'm not so much of a quantum guy, so it's just more the guys I work with, the guys in Nottingham. I see that there's analogy with the Zeno effect. So the Zeno effect where you measure either partially or completely as a projective measurement, and then you try to squeeze the system or locate the system in a particular state by doing a repeated measurement. It's similar, but I think it's different at the same time. So I would see Xeno measurements closer to projective measurements, and this one a kind of intermediate between the Lindblad and the projective measurement again.
Because
But this is something
also,
that yeah, it might have been studied. I'm not so sure actually. Michael Kastner would know more about this.
yeah, because also Camille said that to complete the question or comment, even though you said that reset process is different from the measurement, the curves looks like Zeno effect curve, and that's probably true. Yes, I mean the Zeno effect curve looks like this.
Okay,
Long
I would be interested to have a look, but I haven't dug into that analogy myself.
Okay.
That's all questions.
Good.
Yeah, and Ilya, thank you very much for
the
moderating the questions. And I just see that we went a little bit over the optimal 1 hour, so it's time to reset the webinar for the next one. Yeah. So Hugo, thank you so much for the very interesting talk. And I think through the question we heard that there is potential for further development. Yeah. So maybe some of the participants will stay in touch with you, including me, and we will see what we can do. And maybe just an advert. Tomorrow morning we have a data breakfast where the quantum mathematics team of the University of Copenhagen will share with us what they're doing around COVID. So it's another mathematical COVID talk. And probably the next few days we will announce the next NITheP webinar, which will probably take place today in 2 weeks, I guess. Yeah. So thank you very much to all of you again for participating, and then particularly, of course, thank you to Hugo for his time and for preparing a very nice talk. So thank you very much. Have a good rest of the week, of the day, yeah, and the week, of course, as well. Yeah, thank you. Bye. Bye.
Okay.